So for section 5.6, we're going to talk about compound interest. And this first example here is just to give you a sense of where the compound interest formula comes from. You could very easily just write the formula down and you could use it, plug numbers into it, and be fine. But I'd just like to give a sense of where the formula comes from using kind of a real example. And then after we look at the compound interest formula, we will extend that to interest calculated more than once per year, all the way up to what's called continuous compound interest. So hopefully after this first example, we'll get an idea of where the formula comes from and then how to use it. So let's suppose that $1,000 is deposited in an investment that earns 8% interest per year. So what that means is interest would be calculated once a year, and then at the end of the year, you will have your original investment plus the interest that is earned. So in this case, looking at 1 year, you would take $1,000, which is the original investment, and you would add to that 1,000 times 0.08. That 1,000 times 0.08 is what your interest will be. So you earn 8% on your investment, and that gets added to your original investment. So after 1 year, we'll have $1,080. It's not too difficult to see. I'm going to do one little algebra step here. So if I factored out $1,000 from each of those terms, what you'd see is this becomes 1,000 times the quantity, 1 plus 0.08. And on the surface, again, that might not look like that's really important, but you'll see how that's used when we talk about 2 years and then extend that beyond 2 years and come up with the general formula. So still the same number, 1,080, but you can write it this way as well. $1,000 is your original investment, and instead of adding 1,000 times 0.08, it's the same as multiplying by the quantity 1 plus 0.08. And you'll see how that's going to come into play here when we generalize this formula. So let's consider 2 years. Now for 2 years, your investment heading into year 2 has now grown to $1,080. So that's what the calculation is going to be based on. So it's going to be 1,080 plus 1,080 times 0.08. So you're calculating 8% of your new amount, which is 1,080, and adding that to your new amount. So after 2 years, you'll have $1,166.40. Now if I do the same algebra step, factor out 1,080, it becomes 1,080 times 1 plus 0.08. Now going back to what we had in year 1, I can take 1,080 in my year 2 calculation and replace that with 1,000 times 1 plus 0.08. You can see that I'm doing that here. Now if you look at it, my year 2 calculation can also be thought of as 1,000 times the quantity 1 plus 0.08 times the quantity 1 plus 0.08, which I can simplify to 1,000 times 1 plus 0.08 squared, which still gives you the same amount. Now you think about it, look at the way that formula is written. 1,000 would be my original investment before any interest is calculated. 0.08, which is on the inside of that quantity, is actually my interest rate, and 2, the exponent, is the number of years that money's been in the account. So if I want to generalize that for any number of years, so if you look, we're asking for the amount after t years. In this example, it would be 1,000 times 1 plus 0.08 to the t. So if the question was, how much is in the account after 12 years, you wouldn't have to calculate the interest after 1 and then take that amount and calculate it for year 2 and then take that amount and calculate it for year 3 and so on and so on. You can just take your original amount, your interest rate, and raise that to the number of years that the investment has been earning interest. And that is kind of giving you a sense of where the formula comes from, because if I want to think about a general formula for any compound interest calculation, here's the formula. It is A equals P times 1 plus R to the T. The only thing we've added to what we had previously was turning it into an actual equation, A equals. So I'm just going to identify what each of those parts is. A would be your amount after a certain number of years, the amount you're looking for usually. P would be your principal or your original investment or your original loan, if you're talking about how much you would owe after a certain amount. R would be your interest rate, and T would be however many years the investment or loan has been earning interest. And again, one thing I want to point out is that r will always be your interest rate as a decimal. So that is the very basic compound interest formula, and hopefully that going through a quick example kind of gives you a sense of where that comes from. So now let's walk through an example. Now that we've kind of looked at the formula, let's walk through an example and quickly just calculate what we're looking for. So let's suppose that $2,000 is invested at 7.5% interest compounded annually, and we want to know how much is in the account after 8 years. So identifying the parts that were given, P would be your original investment, which is $2,000. Interest rate would be 7.5% or 0.075. Just be careful with your decimal there. It's not 0.75, that would be 75%, which is definitely going to make a huge difference in your calculation, and T would be 8. So putting that in the equation, I don't know A, which is what I'm looking for. This is what I have. A equals 2,000 times 1 plus 0.075 to the 8th, which would give you $3,566.96. So that's about as straightforward as a calculation as you'll get. You'll be told your principal, your interest rate, and how long you're looking to keep that money in that account. Another way you could approach these types of problems is be asked how long it takes money to double. A little bit later in this lesson, we'll look at an actual formula for calculating how long it takes for something to double, but here's a very straightforward example. We're talking about double. How many years is asking us time? So that's what we don't know. That's what we'll be solving for. So if the principal is 2,000, we know if that money doubles, we'll have 4,000. So we're essentially looking for how long it takes 2,000 to go to 4,000. So using this annual compound interest formula, the only unknown is T. So if I want to solve for T, I'll divide both sides by 2,000. And then we talked about solving exponential equations in this chapter. When the variable is an exponent, you'd use logs to solve this. Now you can take the log of both sides or the natural log of both sides here. I'm just going to take the natural log. It's a little bit easier to write, just as easy to calculate. So take the natural log of both sides, and what that allows me to do is bring that t, which is what I'm looking for, down front as a coefficient. So this can be written as ln of 2 equals t ln of 1.075. Divide both sides by ln of 1.075, and you would get t equals approximately 9.584 years. So if 2,000 invested at 7.5%, it would take about 9.584 years for that money to double to 4,000. So some straightforward calculations there. Now what we're going to look at here is, what if we want to calculate interest more frequently than once per year? Because in reality, interest is not calculated this way anymore. Most interest is calculated what's called continuously, which is every millisecond of every day. But if we're looking at more simplified examples, interest can be calculated every quarter, which is 4 times a month, every day, every 6 months, which would be semi-annually. There's a lot of different what we call compounding intervals. So what that does is adjust our compound interest formula a little bit. So here's an example. $1,000, 8% annually again, but we're going to calculate interest a little bit more frequently. So the first one we're going to look at is quarterly. And so how does that change our equation? So it is important to understand the word. Quarterly means 4 times a year, monthly means 12 times a year, annually means once, semi-annually means 2. So you'll need to be aware of kind of what those words mean in intervals. So basically the number of times interest is calculated per year. So the quarterly example, the formula is very, very similar. The difference though is instead of A equals 1,000 times 1 plus R to the T, we have to consider how compounding interest more than once per year affects our formula. And the most straightforward way I can explain it is you take your interest rate, which is 8% yearly, and you divide it by how many times your interest is calculated in that year. So you take 0.08 in this case divided by 4. Now if you were to just raise that to the first power, what that would do is turn your interest rate from 8% to 2%. So that's not what really happens. It basically when you compound interest more than once per year, you take your interest rate divided by the number of times it's calculated, but you also need to multiply your exponent by that number. So you're reducing your interest rate by a certain factor, but also multiplying your time by that factor, and it, you'll see how that slightly changes the number a little bit, but also doesn't drastically affect the formula whatsoever. All it does is add denominator on your rate, and then that same number goes in the exponent spot. So what this would become is, again, 4 times per year. That's where that 4 came from. So $1,000 at 8% with interest calculated 4 times a year would give you $1,082.43. And what you should hopefully remember from the example at the very beginning, which was $1,000 at 8% once a year, that was $10,080. So calculating interest more times per year actually increases the amount that your money earns, because the more frequently you calculate interest, the more interest that gets added to your amount. Now, it doesn't increase forever, and we'll talk about that in a little bit, but $1,082.43. Now, what if I were to compound interest monthly, so 12 times a year? Very similar setup, obviously. A equals P, which is your initial investment, and then instead of 1 plus R to the T, it's 1 plus my rate divided by my compounding interval, which is once a month, or 12, raised to the 12 times 1. So please be aware that 12 times 1, or 12, is all in the exponent spot. When you type this in your calculator, I would just type this exactly like it is into my calculator, and what I'll get is a little bit more than 1,082. Actually, I'd get 1,082.99, so a few cents more, because it's still only 1 year, still 8%. We're just increasing the number of times that interest is being calculated. So what is the general formula for that? For T years and N times, this is what you'll see as your compound interest formula. So when interest is calculated once a year, it was just 1 plus R to the T. And now if you think about it, if you put 1 in for N in that equation, you would have the exact same formula. So this is really your compound interest formula for any number of times that interest is compounded. So it could be, like I said, once a month, which is 12, once a quarter, which is 4 times a year, semi-annually, which is twice a year. So N is always going to be the number of times that interest is calculated. So that's the only really new variable in our compound interest formula. And then one thing to consider is, if N is how many times it's compounded per year, and T is how many years the account is, collecting interest, then N times T would be the total number of times interest is calculated. For instance, if interest is calculated 12 times per year for 12 years, N times T, that exponent would become 144, which is essentially the number of times that interest is being calculated. For this next example, we're going to look at the difference between what's called nominal interest rate and effective interest rate. And the basic explanation between the difference is your nominal interest rate will always be your listed interest rate. So for instance, if a problem said you invest a certain amount of money at 7% interest compounded monthly, then 7% would be your nominal rate. Now, when we talk about effective interest rate, what that essentially does is take your nominal or listed rate and convert it into a rate that converts a rate that's being compounded more than once per year into what that rate would be if it were compounded once per year. So basically the way I think of effective rate is it considers the number of times that interest is being compounded, and usually increases your nominal rate. So if I have a 6% nominal rate, then my effective rate should go up the more times interest is calculated. Now, it's not going to go up forever, but it should be more than what the listed rate is, because we saw in the previous example, when we compounded interest 4 times a year versus 12 times a year, the 12 times a year had a slightly larger amount in the account after a year, just by increasing the number of times that interest is calculated. So here's a really quick example. If the nominal rate is 6%, what would be the effective rate if interest is compounded monthly? And here's how you would calculate that. Now, I don't know my initial amount, P, and I don't know what that's going to be after a certain amount of time, because it doesn't really affect your calculation for nominal versus effective. So I set up the rest of my compound interest, which is 1 plus 0.06, which is my listed or nominal rate, over 12, which is my number of times interest being compounded, to the 12 times t. So to take my 0.06 or my 6% nominal rate and convert it to an effective rate, here's the only part you would calculate is the 1 plus 0.06 over 12 to the 12th. So if I just look at that part and actually figure out what that decimal is, you'll see this looks a lot like my compound interest rate from my very, very first example. So the idea there is if I take a 0.06 or 6% nominal rate and compound interest 12 times a year, if I were to just calculate that part of the formula, I still have A equals P and then some quantity raised to the T. You can see that 1.061678 is slightly bigger than 1 plus 0.06. So it took compounding interest 12 times a month, took a 6% listed or nominal rate, and turned it into an effective rate of 6.168%. So if you're ever asked to find an effective rate for a certain nominal rate, you'd set up your compound interest just like we did in the previous examples, but you would actually just calculate the quantity raised to the n power. You'll still leave t out there. Now, 1.061678, that obviously includes the 1 plus, so you really just subtract 1 from whatever that number is on the inside there, and that should be your effective rate. So again, A and P, which is your amount after a certain number of years, and your initial investment don't affect how nominal changes to effective. So really you're just calculating that interior part of the function, the 1 plus r over n to the nth, and you can subtract 1 from whatever number you get on the inside there, and that would be your effective rate. Now, I already alluded to the fact that you can compound interest really as many times as you want, once a day, once a minute, once a second, but we need to have a name for interest basically being calculated every fraction of time per year, for instance. So here's a quick example. This should maybe look a little familiar when we talked about exponential functions back in 5.2. But let's think about what happens when the number of times interest is compounded continues to increase. So moving from once a year to once a month to once a day, let's see what happens to our interest rate. So if you think about it, let's just come up with an example. So for easy math, let's suppose that we invest $1 at 100% interest rate. So after 1 year, your money will turn from $1 to $2. Now, what would happen if in that same time frame, within that same year, you increase the number of times the interest is calculated? So it's not going to make your money increase forever. There's actually going to be a limit to what your money could become. So quick example would be if interest calculated annually, it'd be A equals 1 times 1 plus 1 to the 1. So that is our compound interest formula. 1 on the outside is your principal, 1 plus, and now my rate is 100%, which is as a decimal 1, raised to the first power. So what I'd have at the end of 1 year, if interest is calculated once per year, would be $2. Now if we calculate interest every quarter, similar setup, 1 times 1 plus, instead of just 1, it's 1 over 4, which is my interest rate over 4 times per year raised to the 4 times 1, gives me $2.44. So more money than $2, which I would expect because I increased the number of times that interest is calculated. Let's look at monthly. Set up my compound interest formula. 1 times 1 plus 1 over 12 to the 12 times 1. I get 261. So still more money than before. But notice the jump between annual and quarterly was 44 cents. The jump between quarterly and monthly is not as much, only 17 cents. So let's look at more frequently than monthly. How about every day in a year? So 1 times 1 plus 1 over 365 to the 365, $2.71, 2.7145. Now I included a couple more decimals. You'll see why here in a second. Now the jump was only 10 cents. So still an increase, but not quite as much. So what you'll see is the more frequently I calculate interest, the more money I'd have after 1 year, but it's not going up forever. It's starting to slow down the increase between each compounding interval. So if we look at hourly, you'll have to trust my math. There's 8,760 hours in a year. and you'd have 2.7181. So more than before, but not quite not a big jump between daily and hourly, even though there's a huge jump between how many days there are in a year and how many hours there are in a year. So I'm going to look at minute, one more. Now I could keep going, obviously minute, second, millisecond, but you'll see kind of what's happening if I looked at a minute. So again, trust my math. There are 525,949 minutes in a year. So if I set up my compound interest formula for every minute of every day of every year, I get 2.71829. Now, hopefully, if we're paying attention earlier in this chapter, that number should start to look pretty familiar. So 2.71829 looks a lot like E. And actually, where E came from, we know we talked about it a little bit before, but I just gave you the function before and said this is where E comes from, but it really came from this compound interest calculation. The more frequently you compound interest, the more money you'll have, but there's a limit to that, and actually that's where E came from. So if you think about compound interest, and I increase the number of times that interest is calculated, it's going to approach a specific number, which is E. So what that means is, if I think of interest calculated what we call continuously, which is as frequent as you could possibly get, which is every millisecond of every day of the year, the compound interest formula changes a little bit, and what it is you've seen it before. A lot of people call it PERT. So it'd be A equals P times E to the RT. So no longer do I have a quantity of 1 plus R over N to the N. All that gets wrapped up in E to the R. So E comes from the limit, essentially, of how many times you can calculate interest in a year, and then you raise that to your rate times time. So what you need to be looking for is problems where the word continuously shows up. So we'll look at this next example, you'll see what I'm talking about. So we're going to look at an example, and we're going to contrast compound interest with continuous compound interest. So if we look at semi-annually, so $1,000 placed in an account earning 6.25% annual interest, or a nominal interest rate of 6.25%. So here the question is, how long will it take for the account balance to reach $5,000? And we're going to look at two different interest calculations, semi-annually and continuously. So we're still looking for a time, but we're looking for a traditional compound interest calculated twice per year versus a continuous compound interest. And what you should see is, if interest is compounded continuously, it should reduce the amount of time it takes your money to grow to $5,000. So let's verify that. So set up the compound interest formula for semi-annual interest. So 5,000 equals 1,000 times 1 plus 0.0625 over 2 to the 2t. So 2 again comes from my semi-annual interest, and I'm going to solve for t. So I divide both sides by 1,000, and then it also, in my calculator, calculate the 1 plus 0.0625 over 2, and I get 1.03125. Now, that number happens to be exactly 1.03125, but if you're going to be doing these types of problems and that decimal doesn't terminate like this one does, what I would do is, in your writing, you don't have to write the entire decimal, but in your calculator, you should definitely not ever round until the very, very end. So what I mean is, all throughout your calculations in your calculator, you should be using the unrounded decimal, because if you don't, then your answer at the end could be off by, depending on how long the interval is, 10 cents, 20 cents, and that'll definitely make a difference between a right and wrong answer. So 1.03125 is the decimal that it comes out exactly to be, but if it does go on to the end of your calculator screen, you don't have to write the whole thing. I'd go at least 3 or 4 decimals in the writing, but definitely don't round until the end. Only round once and only round at the end. That being said, to solve for t here, I would take the natural log of both sides, and then I would, that allows me to bring 2t down to the front. Now you could also take the log of both sides. I'm not using, natural log is fine. You could use log or natural log. For continuous compound interest, I would definitely use natural log, and you'll see why, but I'm just writing natural log. That's the log function I'm going to use. You could use log base anything. in reality. But now I brought 2t down in front, and then I'm divide both sides by everything that's not t. So what that'll give me is t equals ln of 5 over 2 ln of 1.03125, which would be approximately 26.151 years. So if interest is calculated twice a year at 6.25%, my money would go from 1 to 5,000 in a little over 26 years. Now, if I were to look at continuous compound interest, the formula is a little bit different. So continuous means you should be using E. So 5,000 equals 1,000 E to the 0.0625t. Same thing, I would divide both sides by 1,000. Now, I would definitely take the natural log here because I'm using E as my base. Taking the natural log of the right side will definitely simplify my calculation quite a bit. If I take the natural log of both sides, what I'll end up with is natural log of 5 equals 0.0625t, because natural log of e to any power will always be the power. And if I divide both sides by 0.0625, I would get t to be approximately 25.751 years. So a little bit less time, maybe about half a year. So that's how increasing the number of times interest is calculated either yields you more money in the long run or shortens the amount of time it takes to reach a certain amount. They're both the same thing, so just showing you same amount, same interest rate, but different compounding interval, continuous versus semi-annually. Now, if we want to contrast nominal and effective rates with continuous compound interest, it's kind of the same idea. How much I put in the bank and what it's going to be at the end is really not going to affect my calculation. If I want to look at a nominal rate of 8% and I want to figure out what the effective rate is, all I really have to do is compute the e to the 0.08 part. And what that'll be is, a decimal. So you'll see what that gives me is p times 1.083287 something 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 to the t. Similar to before when I was just calculating the 1 plus r over n to the n part, I'm just going to compute the e to the 0.08. What that gives me is 1.083287, and then the effective interest rate part will essentially be how much above 1 that is. So if I subtract 1 from the inside of that quantity, that'll give you your effective rate. And again, if I take an 8% annual interest rate and I compound interest continuously, it essentially increases my nominal rate to an effective rate of 8.3287%. Now, part B, you're given the effective rate, you want to find the nominal rate, so you're essentially working backwards. So here's a really, really straightforward way to set it up. If I take 1.08, which would be the inside of my e to the r, and I set that equal to e to the r, that would be, if I solve for r, that'll tell me what nominal rate would give me an 8% effective rate. So hopefully that setup makes sense. If you think about what I did in the previous problem A, e to the nominal rate gave me my effective rate. So I have my effective rate, I can set that equal to e to the r and solve for r. So if I take the natural log of both sides, I would definitely use natural log here because I'm dealing with e. So the natural log of 1.08 should be my effective rate, or excuse me, my nominal rate, which is 0.07 or 0.07696. Forgot my zero there. So 0.07696, which is a nominal rate of 7.696%. And as I mentioned before, I want to talk about doubling time. I'm going to give you two formulas here. One for calculating exactly how long it takes money to double, and then one we call the rule of 70, which is a way to approximate that. So if you want to know what doubling time is, there's a very straightforward formula, but if you know me at all at this point, I don't like to just give formulas and say, here you go, remember it, plug it in. I'll give you a really quick way to show you where it comes from. So if you consider the compound interest formula, which is A equals PE to the RT, if you think about doubling, what that means is after a certain amount of time, the amount I have at the end, A, should be twice what I put in. So if my money doubles, A is equal to 2P. So I can really write this as 2P equals PE to the RT, divide both sides by 2, or excuse me, divide both sides by P. So I get 2 equals e to the rt. And what I'm looking for is to solve for time, essentially, because I'm trying to figure out how long it takes my money to double. And what you'll notice is my a and p are gone. The however much I put in, I know the end is double that, so I'll always have 2 on the left side. 2 equals e to the rt. So if I take the natural log of both sides, I would get ln of 2 equals r over rt, divide both sides by r. So there's your formula, ln of 2 over r. Now, r is a decimal in this case, so if you're ever asked, calculate how long it takes for a certain amount of money to double if the rate is 7%, you would go straight to this formula. ln of 2 over 7% is a decimal, so 0.07 or whatever it is. So this is a very straightforward formula for figuring out exactly how long it takes for something to double. Now, there's the rule of 70 is a way to approximate that. So a quicker calculation, which gives you a rough idea of how long it takes the money to double, which you could maybe do without a calculator. And I'll show you what I mean. And here's where this rule comes from. It's not that big of a stretch. It's very closely related to your doubling time. So if ln of 2 is about 0.7, so if you plugged in your calculator, ln of 2, you'd get about 0.7. So if you think of 0.7, or if you think of your doubling formula, ln of 2 over r, and you think of ln of 2 as 0.7, then that means your doubling formula can be approximated with 0.7 over your rate as a decimal. Now again, I don't have, if I didn't have a calculator and I wanted to approximate it, I could say 0.7 over your rate as a decimal. If you just multiply the top and bottom by 100, you get 70 over your rate as a percent. And what that'll do is give you a really quick way to figure out how long it takes your money to double approximately. So quick example would be if I put a certain amount of money in an account at 10%. Well, using the rule of 70 over 10% would be about 7 years. So it gives you a rough idea how long it takes for your money to double. And if you want to calculate exactly how much, you would take the natural log of 2 divided by your rate as a decimal. So both of these they're connected, they go hand in hand, but one is used for estimation, rule of 70, and one is used for exact calculation. So this next and last example will kind of show you that. So consider we had $2,500 invested at 8% compounded continuously. So for part A, it says estimate how long it'll take for the account to double. That means use the rule of 70. So here would be the setup. I'd take 70 divided by my rate as a percent. So 70 over 8, you could probably come up with what that would be approximately. Actually, should maybe come up with that without a calculator. So 8 goes into 78 times with 6 left over. So you get 8.75 years. So without a calculator, you get an idea that it would take almost 9 years for your money to double if you invested your money at 8%. Now to calculate exactly how much that doubles, I would take the natural log of 2 and divide it by my rate as a decimal, which would be ln of 2 over 0.08, which would be 8.664 years. So you can see they're fairly close. One is something you could do, maybe in your head without a calculator, and the other one is calculating exactly how long that would take. And neither of them take into account, nor does it matter how much money you put in the bank, because if we're going from a certain amount to twice that, then if you put $1 in or $1,000 in, you're still going to end up with 2 equals e to the rt, which is why ln of 2 over r will always work, and rule of 70 will be just a quick way to approximate that. So that's all that we're going to look at for now for compound interest. So we have a compound interest formula and our continuous compound interest formula. Definitely need to know how to use those to solve for a certain amount of money or solve for a certain amount of time, and then also effective versus nominal rate. So 5.6 homework assignment should be something you can accomplish, and I hope this video was very helpful.